to the second part of the morning session. So first speaker of the second part is Sandro Donadi from Queen's University, Belfast, and he's going to talk about underground test of gravity-related wave function collapse. So, Sandro.
Okay, thank you. Thank you, everybody, and well, we will arrive. Thank you, everybody, and first of all, I would like to thank the organizer for this nice conference. Also, for me, it's the first time I have occasion to visit Brazil, and I'm really enjoying the people, the vibes, so thank you also for this opportunity. What I'm going to talk today, essentially, is the Diosy-Penrose model, and a test that, how it's possible to test the Diosy-Penrose model by measuring radiation emission. So the structure of the talk will be the following. In the first part, I will introduce the model. In the second part, I will discuss about the experiment that was performed at Gran Sasso Laboratories 3 years ago. And in the last part, I will discuss about some recent developments. So to introduce the model, I always start from a slide on the measurement problem, because the Diosy-Penrose model, like all other collapse models, were introduced to solve the measurement problem. So the measurement problem in quantum theory is given by the fact that in the classical Copenhagen orthodox formulation of the theory, we have that the state vector evolves according to two dynamics. On one hand, you have the Schrödinger equation, which is linear and deterministic, and on the other hand, you have the collapse, which is nonlinear and stochastic. And the problem with quantum theory, with the standard formulation that you can find in textbook, is that it's not really clear when one has to use one dynamics or the other one. So in the very postulate of a theory, you find words which are ambiguous, like observer, measurement. And I think this was summarized very well in this quote by John Bell. And the question is really, if you take this approach, what exactly qualifies some physical system to play the role of a measurer? Why at some point some system cannot be included in the Schrödinger equation, but they follow descent rule and they induce the wave function collapse? So this is the measurement problem. The standard Copenhagen formulation does not provide an answer to this. So the possible interpretation have been introduced. Yesterday there was some discussion after the second talk about Bohmian mechanics, which I also personally like. But today I'm going to talk about the different possibilities, which is the one given by collapse model, and in particular I will focus on the Diosy-Penrose model, which is a particular kind of collapse model where the collapse is related to gravity. So the main idea in collapse model is, we saw that there are these two dynamics, is to merge them together. So essentially you modify the Schrödinger equation by adding some extra term which describe a wave function collapse. In this way you don't have anymore two different dynamical laws, but you have one single equation which is true for any system, whether it is a single electron or a macroscopic system like a cat. And well, once you want to start to modify Schrödinger equation and having this kind of program in mind, there are some things that should be fulfilled, some feature. The first one is that, of course, we want that the modification of the Schrödinger dynamics should be small for microscopic system, because we know that quantum mechanics works well for particles or small microscopic system. At the same time, the effect of the collapse term should become dominant when we have a macroscopic system. The second point is that the evolution, the change of the equation for the state vector must be nonlinear, because if you keep a linear equation, then you cannot have collapse. And the third point is that you also have to introduce stochasticity, and in a precise way, because if you just have a nonlinear and deterministic equation for the state vector, then you can always find a way to use these dynamics to do faster than light signaling. So if you want to avoid signaling, then together with nonlinearity in the evolution for the state vector, you must have also stochasticity. This was proven by Gizen in this very nice paper of 1989. And in this respect, an example of a nonlinear and deterministic evolution is the Schrödinger-Newton equation, but yesterday there was a very nice talk at the end of the day about this equation. And indeed, the Schrödinger-Newton equation suffers this problem of which it can be used to generate superluminal signaling, at least if you take it as a fundamental dynamics. Okay, now I'm just introducing the continuous spontaneous localization model as an example of collapse model because it's a reference model in the literature, but apart from this slide, then I will move to Diosy-Penrose, but most of the features of this model are true also for the Diosy-Penrose model. So in this model, the equation for the state vector is given by this long two-line equation. And as you can see, we have the standard Schrödinger term, but then we have these other two terms which describe the wave function collapse. This mu here is the mass density operator, and these two terms fulfill the two characteristics, the two requirements I mentioned in the previous slide. We have stochasticity, which is contained in this W. These W are a family of Wiener process. You have one for each point of space. And it's also nonlinear because this bracket means the expectation value of the operator on the state psi at the time t. So, and one can prove that the effect of the second and the third term is exactly to collapse the wave function in the eigenstate of this operator. In the case of a CSL model, we have also two new parameters introduced. This is a phenomenological model. Lambda somehow gives you the strength of the collapse, and RC the length above which the collapse becomes more effective. But again, I don't want to enter in detail for this model because the focus will be on DP model. The important thing, which is true for any good collapse model, is that it should localize in space. And there is an amplification mechanism. So this amplification mechanism means what? That whenever I have here a composite system, then essentially the rate of collapse for the composite system grows with a number of constituents of a system in a precise way. And this comes out of the equation. So it's not that I change the lambda by hand. It comes naturally out from the equation. So if you take this lambda very small, you can have that the effect for a single particle of this collapse term is negligible, which is what we want. But when you start to have a number of Avogadro of particles, then it becomes dominant. And this is the amplification mechanism, essentially. Also, to conclude on CSL model, given this equation for the state vector, one can find the corresponding master equation, which is this one, is of a Limblad form. So again, you have the unitary part, which comes from this, and then the other two terms provide you this Limblad term. You see, all the nonlinearity cancel out essentially because of the presence of the stochasticity. And the equation is Markovian, essentially because here you have Wiener process. You may also consider non-Markovian generalization, but this is another, I'm not going to discuss this today. So let's move to the Diosy-Penrose model, and actually here I call it Diosy model because it was introduced originally by Diosy. And as you can see, the structure is extremely similar to the one of the CSL. Again, you have the Schrödinger term and the other two terms which describe the collapse. The main difference is that instead of having the Gaussian function that was there for the CSL model, here you have the correlation of these noises is given by a Newtonian potential. And the other nice feature that the model had, at least in this original formulation, is that here you don't have three parameters. There is only G, but you don't introduce some phenomenological parameter. Now, given this model, again, one can find the corresponding master equation. I'm showing the master equation because it's also often very useful whenever you want to compute expectation value of operator, you can just work directly with this one. You don't need to solve the nonlinear dynamics. So it's useful to have it. And also this can be useful to see how we can estimate the time of decay of a superposition in this model. And the way to do that is one can neglect the unitary term, so just to focus on the effect of the collapse, and then the equation can be solved very easily, and one can show that if you take the matrix element, these A and B are two different positions in space, the matrix element decay exponentially with some time tau, which is given by this formula. I'm showing it here because this then shows also the connection with the Penrose proposal, and is the reason why now the model is known as Diosy-Penrose model. Yeah, let's move to Penrose proposal. So essentially, Penrose, first of all, is also troubled by the measurement problem of quantum mechanics, and he also thinks that there is some incompatibility between general relativity and quantum mechanics, and in particular between equivalence principle and superposition principle. There is a very nice discussion in this more recent paper on this point. And essentially his idea is that when I have a mass in a superposition, this will generate two different space-time curvature, and when this difference becomes too large, nature somehow cannot tolerate it anymore, and it will make it collapse. And he provides a way to quantify what does it mean large in terms of an energy, which is computed in this way. So imagine that you have this large mass in a superposition, and then at some point R, you put a probe. Now the probe will fill a superposition of two accelerations, the one generated by the mass around the point A, and GB generated by the mass around point B. And you see, this already makes problematic to, for example, find a local free-fall frame, because if I go in the free-fall frame that cancel GA, I don't cancel GB, and vice versa. And so the idea is that to measure the tension between these two different space-time, you just take the difference of the two, then you square it because you don't want that positive and negative differences cancel each other, and then you sum over all the points of space, because there is no one point more important than other. And okay, you have to add this 1 over G in order to get energy dimension here. And the thing is that this formula then can be just rewritten using Newton's law and Poisson's law in this form. And if you remember, this was exactly the same form that we saw for the Diosy model. So Penrose somehow arrived at this formula in a different way compared to Diosy, but they predict the same time of decay of a superposition, which is why the model is known as Diosy-Penrose model. The time, in the case of Penrose, is basically h bar divided by this delta E. And now, okay, I put many equations, but let's see some example just to get a feeling of what the model tells. Now, if you put the number for the proton, so with this mass and this radius, then you find out that the time of decay of a superposition of a proton is of order of millions of years, which is what we want, because we know that a proton in superposition will stay stable, will not collapse spontaneously very quickly. But on the other hand, if you use the same formula I showed before for a dust grain of the size of 10 micrometers, so from quantum perspective is huge, but it's not even so huge. It's not like a planet. It's still micrometer size. Then you find out that the time of collapse is 10 to the power minus 8 seconds, which means even if you manage to put this in a superposition, according to the Diosy-Penrose model, will collapse in this very, very short time. So this just to say that with this model, you don't need to go to Planck scale or that kind of extreme value to see some effect. Now, until now, the model, the Diosy-Penrose model, there are no free parameter, and this was originally thought, but there is an issue with this choice that if you consider a point-like particle, like could be an electron, then no matter how small is the mass of a particle, the collapse will be always instantaneous. And we know that this is basically already falsified because we can do interference. And in order to cure this problem, which is essentially due to the divergence because of the Newtonian potential, people suggested to put a high energy cutoff in a form of a mass density, the spread of a mass density, which is given by a parameter R0, which has the dimension of a length. And so, in the case, Diossi suggested a value for this R0, which was 10 to the power minus 15 meter. He had in mind that the main responsible for this collapse are proton and neutron, so this was the natural value to suggest. Well, Penrose relate this R0 to, the whole story is that it is related to the stationary state of the Schrödinger-Newton equation, but for system relatively simple like crystal, then it is essentially, he showed that it can be related to the size of a psi square. Now, the proposal of Diossi was immediately ruled out 1 year after by Giraldi, Grassi, and Rimini. Essentially, they show that even if you take a mass density of this size, the Diossi-Penrose model will predict a spontaneous heating, which is in effect I'm going to discuss in the next slide, but it is one of the predictions of the model, which is completely incompatible with our observation. The universe will be much more hot. So R0 should be much larger than this value. Well, the one of Penrose for a long time was kept valid, and this was also having the merit that somehow was not introducing really a new parameter, was still relating it to the size of the wave function, so you didn't have this extra parameter. Okay, now we move to the second part, which is about the experimental test. So one crucial feature of all collapse model and also Diossi-Penrose model is that they do prediction different from quantum mechanics. Essentially, you can understand it also by looking at the master equation. In addition to the unitary term, you have this Lambda-Ladian, so that changes all the prediction. And so this model can be tested. This is contrary to Bohmian mechanics on many worlds. You can do an experiment and tell whether they are true or not. And the natural way to test a model which collapse superposition in space would be to do some matter wave interferometry, which is what has been tried, but in general, this interferometric experiment turned out to be very complicated because you need to go to really large masses, so we go back to the usual problem. And then another strategy was found, which is what we call non-interferometric experiment, and this exploits the fact that in these models, collapse comes all the way together with some Browian-like motion that you induce in the system. Essentially, because you have this continuous collapse, this will keep acting on your system, and even if the system is not anymore in a superposition like here plus there, but even if it is in a localized state, unless it's not perfectly in a Dirac delta function, which is never the case, it will always feel the effect of a collapse, and this will induce a Browian-like motion on the system. And then, so if you have some tool that can detect very, very small movement, then this can become a way to test the model, which does not require you to create macroscopic superposition. So this was the main advantage from an experimental point of view. As long as you're very good in making position measurement, you can tell something interesting about this model. Okay, let me go a bit more in detail on some of the interferometric and non-interferometric proposals. So on the interferometric side, there was more than 20 years ago now a very important paper from Marshall, Penrose, and collaborator, which was about putting a mirror in a superposition, a mirror of, I think it was 10 micron size. More recently, again, Penrose with Howell and Fuentes tried to consider what one can do using Bose-Einstein condensate, but again, you will need Bose-Einstein condensate much larger than the one that can nowadays achieve. You need to create a new state with like 10 to the power 10 atom, which is still very hard. or also in collaboration with Hendrik and Mauro Paternostro, Angelo Bassi, Giulio Gasbarri, Alessio Belenchia, and Matteo Carlesso, we considered the possibility of experiment in space. The main advantage of going in space is that you don't need to trap things, and they can free fall for even times of order of 100 seconds. So for example, just the Schrödinger spread of the wave function can help you to create spatial superposition. So these are promising idea, but still far from setting strong bound on the Diosy-Penrose model. On the other hand, the non-interferometric tests, which as I mentioned, they don't require superposition. Well, there was already some bound on the model set by the group of Yanbei Chen by studying the motion of the mass in LISA Pathfinder. More recently, Hendrik and Andrea Vinante studied the spontaneous heating from different sources. So again, because we have this Brownian-like motion, this will predict some spontaneous heating that you don't have in quantum mechanics. And so you can try to use this to set some bound on the strength of the collapse. But the one I'm going to discuss more is the third approach, which is based on radiation emission. And here again, the intuition is very classical. Because you have this Brownian-like motion inducing your particles, if they are charged, they will emit radiation, like in classical electrodynamics, a charged particle emit radiation. This is radiation that standard quantum theory do not predict. So what we did was to compute the theoretical expected radiation from the Diosy-Penrose model, and then compare what was seen from experiments done in a very low background noise environment, which are the Gran Sasso laboratories. Okay, now just an outline of, my main job in this collaboration was to do the theoretical calculation, so an outline of how they have been done in this paper, and in the next slide I will show a better way to do them, but here we wanted to keep it fully quantum. So here essentially you have the joint master equation, which gives you the evolution for, before. What we want to compute is this radiation emission rate, which is telling you how many photons are emitted per second at some energy or frequency, as you prefer. So the central quantity to compute is the number of photons emitted at time t with some wave vector and polarization. So to compute this, we use this joint master equation. This is the unitary evolution, and this is the contribution due to Diosy-Penrose. It's written in a different way compared to before, but it's the same thing. The unitary term also was not trivial, because you have the Hamiltonian of the crystal, but then also the free electromagnetic field and the interaction with the electromagnetic field. So overall, there were quite something to put together. An exact calculation, at least with this model, is not possible. So what we did was use a perturbative approach with respect to the Diosy-Penrose term and with respect to the electromagnetic interaction. And after several calculations, you end up with this formula in this red box for the radiation emission rate. Now, first of all, this formula, I will explain why, but it's not valid for all possible photons. It's valid for photon with wavelength emitted, which is in this range. So essentially, you need the wavelength to be smaller than the atomic size, but larger than the nuclei size. And what this emission rate tells you is that, first of all, the emission goes as 1 over omega. So the higher the energy of a photon, the lower the emission. The dependence also on this mass density spread at 0, this free parameter, is very strong because you have a R to the power cube. This Na is the number of atoms in the crystal. So this formula refers to the emission from a crystal. In particular, we were interested in a germanium crystal. So clearly, the radiation emission grows with a number of atoms. That is intuitive. But it also grows linearly with the atomic number. And the reason for this, and also the reason for why the formula is only valid in this regime, is the following. Imagine that you consider the emission of a photon with a huge wavelength, like 1 meter. then essentially the protons and the electron in the same atom will emit coherently, and the emission from proton and the one electron cancel each other, and so you get zero emission. So in order to avoid this cancellation, you need to reduce the wavelength of the emitted photon to a point that it can distinguish between electron and nuclei. And when this happens, which is exactly in this regime, electrons emit independently, incoherently with respect to the protons, while protons emit coherently because they are still confined in the nuclei, and this gives rise to this square factor, which in case of germanium, n is 32, so having 32 squared is not bad. You get more than one order of magnitude. Okay, this was the quantum mechanical complicated way to do the calculation. There is another one which I personally like more and is also closer to the intuition of the process, which is the following. You can start from the Diosy-Penrose master equation, because you just need the master equation to compute this quantity. You don't need other stuff. And build what is called a unitary unraveling. So given a Limblad master equation, you can always find, as long as the Limblad operator are admission, you can always find a unitary unraveling of this form, and where essentially you encode the effect of the Diosy-Penrose in this random potential. And here is the form of a random potential. This one is for the Diosy-Penrose, the one on top was for CSL, I put it for completeness. So clearly this equation, just to be clear, does not collapse the wave function. This is not the Diosy-Penrose model. But as long as you're interested in computing expectation value of observable, you can also use this evolution and you will get the same result with this V given by this. At this point, we can do one more step. We can consider this is a potential, so we can think in a classical term. And given a potential, I can compute the corresponding acceleration just by taking the gradient, essentially. And given the acceleration, we can use Larmor formula. And the Larmor formula will give the total power emitted, which can be related to the radiation emission rate. When you do this, which is much easier than the quantum mechanical calculation, you will get precisely the same emission rate. This is kind of proving that this effect is really classical, this radiation emission is. You can reach precisely the same result by using this classical approach. Okay, now let me move to the experiment. So the experiment was done here in Italy at the Gran Sasso laboratories. As you see, it's a beautiful mountain. It's 1,000 meters tall or more. So it's good because it can cover from cosmic ray and many other influences. And this is a scheme of the setup. By the way, on Friday, Christian Piscicchia will talk about this more in detail. He was the one performing the experiment together with Catalina Culceano and Matthias Lauberstein. But I just want to give an idea. So this green one was the germanium crystal. Around there are some other shield of protection of copper and lead to further isolate it, because essentially you want to reduce as much as possible all other sources which can induce photon emission. You just want to see the photon if there are due to Diosy-Penrose. And on the right, you see the result of the experiment. The black line are the data, while the green line is a simulated background. So these include some effects which were well known to be there. And the amazing thing, at least I find it amazing, that when you remove from the total count the one that we can simulate, you are left with basically 70 counts, so 70 photons detected in 2 months. It means a rate of 1 photon per day, more or less. And this extremely low rate allows us to put a very strong bound on this parameter at 0. The bound is a lower bound because essentially it's telling you that at 0 must be larger than this quantity. Why? Because if it was smaller, we would have seen much more many photons, not 70. We would have seen maybe 100 or 200. And this bound turned out to be is the green one here, almost 3 orders of magnitude better than the other two. By the way, also the other two were due to non-interferometric experiment. So, as I was saying before, the non-interferometric experiment works better for this kind of model, at least for now. And also with this value, with this bound, we excluded also Penrose's proposal, because when you compute the R0 according to his prescription for this crystal, it turned out to be 1 order of magnitude smaller than the bound that we found. So in this sense, the parameter-free version of a model where this R0 was related to this is not valid anymore. Later, 1 year later, our result was also improved by Mariana collaboration, which repeated the same experiment, but with a crystal which was 40 kilo instead of 2. And so they could place 1 more order of magnitude better bound. Okay, so how much time I have? Just to 10 minutes. Okay, it's good. Now, some more recent developments. As I mentioned before, we studied a certain radiation emission rate for photon with wavelength which is smaller than the atomic radius. What happens if we start to go to lower energy? Because after all, the rate goes as 1 over omega, so one may be interested in trying to go to lower energy. And also, in case of possible non-Markovian generalization of a model, you have interest in going to low energy. Well, the energy we considered before were 100 keV or larger. When you start to go to lower energy, what you find is that the radiation emission rate, so these are not experimental data, these are theoretical calculations. The theoretical formula I showed before gets modified. And the radiation emission rate for both CSL and DP is not anymore the blue line. So the blue line was the prediction I showed before. The emission rate goes as 1 over the energy of the frequency, as you prefer, of the photon emitted. But when you start to go to lower energy, the behavior becomes much more complicated. And this is because what happens is that when the wavelength, lower energy means larger wavelength, when the wavelength start to become a bit larger, some of the internal electron of the atom cancel the emission from the proton. And so the radiation emission rate start to become dependent in a non-trivial way from the orbital of your atoms, and also it will depend on the model. So in this sense, it's also interesting because you see the DP model and the CSL, they do not do anymore the same prediction. I mean, even before they were not the same, but the shape was always 1 over E. Now the shape is becoming much more interesting. So this is something we want to explore more. Also, here we use a semi-classical approach, that formula with acceleration, but I trust to use it until 1 keV. But below this energy, I think one needs to reconsider a quantum mechanical calculation. So this is work for future. Another point which came out because of all these non-interferometric tests, and also in the view of finding some relativistic generalization of Diosy-Penrose and other collapse model, some of the presence of this heating, of this diffusive effect is problematic. And so one may wonder, I mean, in this model, this is there because you postulate an equation where you add by hand linear processes, so it's not a surprise that there is this effect. But then one can ask, can I describe a collapse of a wave function in space without having this heating effect, this diffusive effect? So something more clean, like I have a superposition, it collapses, end of the story. So I think this is an interesting question from a phenomenological, but also from a more fundamental point of view, is can I have collapse without diffusion? So we try to answer to this question, and what we found is the following, that under very general assumption, the answer is no. At least I think these assumptions are fairly general. Thank you. The first assumption that we do is that we don't want our dynamic to allow for faster than light signaling. And this means that there is a linear map for the evolution of your statistical operator. Then we require the complete positivity of the map. Again, we don't want that when we put an ancilla, entangle an ancilla with our system, then the dynamic is not positive anymore. And the requirement of space translational covariance. So essentially the collapse should not change if I just translate in space. Now, if you just require these three things, then what we show is that if you have collapse in space, for sure you will have diffusion in momentum, or at least change of the average momentum, one of the two. So it seems that also these non-interferometric tests are not so indirect. Somehow, as long as you want to go beyond Copenhagen and not just postulate the collapse, but try to give it some dynamics, you end up having this diffusive effect under very, very general assumption. Finally, until now I discussed about the lower bound, so what experiment tell us about this parameter at 0. And this is exactly the area which was excluded by this radiation emission. But one may also, I mean, whenever you build a collapse model, on one hand, you want it to be compatible with observation, and that is what we checked with comparison with your experiment. But on the other hand, for the model to make sense, you want the model to collapse macroscopic object. Because if you have a collapse model which can let, I don't know, a chair like this one in a superposition of here plus that for 1 year is essentially useless. So, because of a theoretical request that you asked for the model to make sense, you may also put an upper bound on L0. So L0 cannot be 10 million of kilometers, because then your model will not collapse anything, essentially. Okay. So we try to check how well the Diosy-Penrose model collapse macroscopic system. And you see here, while the bound from experiment are very sharp, this kind of bound one has to be more careful, because it then all depends on what do you mean by macroscopic. So one possible object that was considered before in the literature and that we considered was to consider a graphene plate of a size of 25 micrometer, because this is a size that can be seen already by a human eye. It's the kind of smallest size. And also, if you require a graphene plate of this size to collapse within this time, which is the human perception time, then what happens is that the prediction of the Diosy-Penrose model is that the time of collapse is always much above this 0.01 second, is always at least of order of 2-3 seconds. So if you want the collapse, the Diosy-Penrose model to collapse this graphene plate within this time, this is not happening. So in this sense, the model does not collapse fast enough. But clearly, I mean, this is arbitrary. One can say, okay, for me, this is not macroscopic enough. So we try to check, okay, how large I have to make this graphene plate in order to collapse within this time. And we tried with different dimension, and it turned out that you need to go to dimension of 1/4 millimeter almost in order for it to collapse. You see here is below this dotted line is the 0.01 second, the benchmark that we put. Also, about the distance of the superposition, in this calculation we always consider the distance to be much larger than the size of the object, because we wanted a real cut state here plus there. But one can ask what happens when I change the distance. But actually, even by changing the distance and even taking it, just look the yellow line of 1 meter, you are still very much above this 0.01 second. Then one can consider, okay, why to get fixated with this planar geometry? I mean, we took this because this is an object in principle visible by human eye, but one can forget about human and just choose another system. And so one can consider a cube. Now, cubes collapse much faster, essentially because matter is closer and I mean, here I'm not showing the equation, but if you see the equation for the time of collapse, it depends a lot on the distance between the particle. And the closer they are, the stronger is the effect of collapse. And essentially what we saw here is that if you see this blue line is the one referring to a cube of a size of 10 micrometers. This was the one considered by Penrose, Marshall in that famous paper of 2003. So if you consider that kind of system and you require it to collapse within 0.01 second, then all this value of R0 from the experimental bound up to here are still not excluded. And so, okay, just to be conservative, we thought, okay, let's maybe put the bound a bit more on the right, but at least it seems reasonable. This is in Armstrong, so 10 to the power 8 is actually 1 centimeter. It seems too reasonable to consider that R0 should be smaller than this, because otherwise, for larger R0, you really need big object which will survive in superposition for much longer. So again, this is not a sharp argument like the one from experiment, but I think it's kind of reasonable to put also some upper bound on this R0, and this turned out to seems a reasonable one. Okay, so in conclusion, we saw that Joseph-Penrose model predicts a spontaneous collapse related to gravity, and this implies a diffusive effect and in particular radiation emission. This radiation emission is extremely powerful in setting bound on the model. Here there is an important point on which I didn't stress, but I want to stress here, that the radiation emission experiments are very effective for Markovian model, but if you just change a bit of the model and make them non-Markovian, okay, I'm done, they will lose, they will not be effective. At that point, the spontaneous heating studied by Vinante and Ulbrich will be much more effective. And finally, we also consider some requirement for the model to collapse sufficiently fast a large object, and when putting all things together, one can safely say that R0 should be a bit larger than the experimental bound, but also probably smaller than centimeter size. Finally, I want to thank the collaborators. So on the top line, we have all the people who collaborated for the part related to the radiation emission experiment. While on the bottom, there is the group in Trieste with which we did the work I discussed in the last two slides on this theoretical bound or upper bound on R0. I thank, of course, also the sponsor, but more importantly, the group at Queen's Belfast University and Mauro Paternostro in particular, and I thank you for being here.
Thank you, Sandro. Questions?
I don't think I really understood the last part of the talk, so let me ask a really specific question. Supposing you take a mirror which weighs 40 kilograms, how long is it going to take to collapse in this theory?
That depends on the value you put to this parameter R0.
This is what I can never understand about the theory. I never get a concrete prediction. I mean, you say R0 can be somewhere between an angstrom and a centimeter, which gives you a large range. Can you not give us a, I mean, because we know that the LIGO mirror apparently behaves according to quantum mechanics, and it's very big. So does this rule out your theory or not?
No, but the LIGO mirror have been used also to test collapse model with this non-interferometric experiment by measuring their position with precision, and they do not rule out, because Lisa find that the bound given by Yen by Chen, it is more powerful, it is more effective than the one given by LIGO. About your question of whether the mirror will collapse or not, I say it depends from R0. If you want, now given this range that I set of R0 going from Armstrong to centimeter, you can take the worst case scenario, take it of centimeter, which means the collapse is the weakest possible that you can have. And then you can compute, and I'm sure that for something like a 40 kilo, the collapse will be instantaneous, but like 10 to the power minus 10 seconds.
Fine, but it doesn't collapse.
What?
LIGO is used
Yeah,
in
but,
such a way.
but LIGO didn't put a 40 kilo in a superposition here plus there.
We'll talk about it afterwards. What I don't understand is that as the years have gone by, the time of collapse for a dust grain has gone, from very short time to now quite long time in this theory, and I just simply have no idea how to understand it.
So I didn't understand the question. No, can you? I didn't listen.
Oh, sorry.
Yeah. Well,
When I first started reading papers about this, it was claiming that dust grains would collapse extremely rapidly. But now apparently that's not the case. And there's a parameter which can be anywhere between an angstrom and a centimeter, which we don't know. So I just don't know how I'm supposed to understand what are the predictions from this theory.
well, for the dust grain, okay, I cannot do the prediction on the spot, but the time of collapse that I mentioned in one of the first slides, that was 10 to the power minus 8 seconds, that corresponds to an L0 of micrometer. Now, if you increase this L0 to centimeter, the time of collapse will get longer, but okay, I should do the calculation, but I don't expect it to become of 1 second. It may become maybe 2-3 orders of magnitude higher, but not. So, the whole point of putting this upper bound on L0 was exactly to say, okay, let's guarantee that objects which are macroscopic collapse sufficiently fast. Actually, now what I think.
I don't even know where the figure of 1 centimeter comes from. I mean, maybe 10 years from now, it'll become 10 meters, just so that the theory doesn't disagree with experiment. This is what I don't understand. R0 was supposed to be very small originally, and now it's already a centimeter.
No, I'm not saying that it's a centimeter. I'm saying that it's within a certain range.
I know, but originally when this theory was discussed, R0 was supposed to be very small. And now you're saying it can be as large as a centimeter, and I don't know why you're saying that. What is the theoretical argument that it could be as large as a centimeter?
The theoretical argument is that, you just introduce this parameter, and then in theory it can be anything.
Right, that's
Okay.
the problem. It's a theory in which the main parameter can be anything.
Yes, but
So
then
you can't make any predictions.
that's the whole point of then putting the bound from experiment, which will give you the lower bound, while the upper bound is by this theoretical requirement. I'm not understanding.
I'm sorry, I have to interrupt the discussion because we have to move on in the program.
Okay.
Yeah. So, Robert, you had a question.
Yeah, I mean, it seemed to me this is a bit like Brand's-Dickey theory. Like when R is infinitely large, then there's no collapse.
Precisely.
Right? So it's a bit like the old Brand's-Dickey theory where you had this parameter and empirically you just keep setting bounds on it. So I take it to mean that now the best bound is R0 is about a centimeter or something. Is that a bound from an experiment or a guess?
No. The bound from experiment is this one.
Okay.
This
So-
one is just from a theoretical argument. You may consider even L0 larger. You can take a 0 equal of 10 kilometer, but then you will not be able to collapse anything, and then the whole purpose of the model is lost.
So all right, so that was partly my question. So what is the largest R0 that can be tolerated before people would say the theory or the model is useless?
This was the whole point of doing this analysis,
Yeah.
and you cannot put a sharp thing because it depends on what
Well,
do
even
you
a
mean.
range, right? Is
As
it?
a range, I would say
A centimeter.
of order of centimeter.
Okay,
Yeah.
thank you.
Okay. So, in order to not put very strict bounds on our lunch interval, let's thank Sandro again.
Thank you.
Okay, so we'll move on in the program. Our next speaker is speaking in Zoom, and